This is the chapter 5 of our content. We're going to discuss the while loops. Before while loops, we have a couple of shorter sections that we're going to discuss. We are first going to see what algorithms are. As you would all guess, algorithms are solutions to our problems, to our algorithms are our internal design of the software we are going to develop. There are many ways of designing algorithms and representing or showing, expressing those algorithms. One of them is a very trivial Blockly solution, as you would find online. For instance, this program here is a simulation of a wake-up process that we encounter each morning. For instance, when some event happens, which is the alarm ringing, okay, when this alarm event occurs somehow, there's a repetition block which is going to be repeated 3 times, as you would all know from the for loops. If the alarm rings for the first time, we snooze the alarm and continue sleeping. And then when the alarm rings again, we're going to go back to the beginning of this process. And as we repeat, this number is going to be decremented. And after the loop is over, that we have hit the snooze button for 3 times, we get a punch in the face. So, or somebody pours cold water, and then we turn the alarm off, and then we get up from the bed, take our shower, get dressed, eat breakfast if we are lucky, and then if the weather is sunny, then we may prefer to walk to school, or this might be our default behavior. If it's not sunny, it might be rainy or snowy, then our parents may be riding to school. So we might take other means of transportation. So this is a very simple algorithm that you might implement. Of course, this is not the ultimate solution to the wake up sequence, but this might be an instance for a specific case. There are some charts that we can use when we design the algorithm. So this one is called a flow chart. We have a lamp here. If the lamp is not working, so when we turn it on, we see that the lamp is not lighting or illuminating. Okay, so we move to this next step. Okay, if the lamp doesn't work, we go to a decision block. The decision block checks whether the lamp is plugged in to the outlet, to the power outlet. If it is not, just plug in the lamp and check whether it works or not. Okay. If it still doesn't work, and as we have already plugged the lamp into the outlet, we move to the yes part of the decision. There might be multiple decisions depending on the decision process. Yes, no, 1, 2, 3, or some other output may come out of these decision processes like this. Okay, it depends on your implementation. And if the lamp is plugged in, as we know, the lamp doesn't work and the lamp is plugged in, so we check the bulb, light bulb, or the LED bulb, whatever it is. And then if it is damaged, we just replace the bulb and check whether the lamp is still working or not. If it is still not working, it was not plugged in, we plugged it in, the bulb was damaged, and it's still not working, then there's a problem with the lamp itself, other than the bulb. So we repair the lamp. The cable might be damaged or the internal parts may be damaged. So this is another simple algorithm for turning on a lamp or repairing a lamp, fixing the problem with our lamp. There are many diagrams. I leave these parts for you to read and find out more of these algorithm design diagrams. This is not specific to algorithms. These charts or diagrams may represent an entire software package. For instance, in one of the projects we had around 120, 150 components as classes and objects. And when the design process was iterating, we had approximately 600 diagrams for analyzing and identifying the relations between those algorithms. Of course, there may be more and more diagrams to be drawn. You could look up the class diagrams representing the objects, the internal structure of your application. There may be similar component diagrams or deployment diagrams for, let's say, which part is going to be deployed at which server, which application container. There may be some activity diagrams, mostly dealing with which part is triggering which other part, or the interaction between user and the computers, and the interaction between different computers, different application servers. There may be timing diagrams, state machine diagrams that represent the current state of the computer, such as this. So this is one state of your computer. If you receive some input, let's say 1, you move to another state, and from there you may move to another state, and from there you might move to this state, or with another input you may move to another state. So this is some basic state diagram for your computer. At each state, your computer has different set of parameters, or your application has different set of parameters. So this is another way of representing the information. These all refer to different situations. So you might have use case diagrams, which is very common. The use case diagrams is that when the interaction starts, you define the paths, the major parts that your process is going through. For instance, you have these stickmen initiating a request, and after that there's a state. So we have these man initiating a process, there's a state or a condition, and after that use case you move to another state, another process maybe, and you can find the examples online. These are not included in the contents of this course, but as exam questions, but they are very important when you're designing your programs. When you start coding right away, there's a high chance of trouble that you're going to encounter when you are trying to express or transfer your code to other people. If you're building an industrial software, a commercial software that needs to be executed or that needs to be audited, inspected by some maybe government offices, you have to provide them the correct set of design documents. So in those design documents, you must use these expressive diagrams and flow charts, other drawings, identifying each step that your software is processing. Otherwise, you might not get a stock exchange compatibility license, let's say. So it's important that you know these concepts when you are going to be working in software projects, especially in the design phase of the process. Most of the time, the developers are expected to draw these kinds of diagrams because they know the solution more than the other people. If you are working in a very, let's say, structured or very organized software companies, some other people might design these problems or these solutions for you, and you're expected to write the software, maybe provide feedback to those design teams so that they can modify their design. But the design has to be consistent with the software at the end of the day. And this is another flow chart. So our computer is not running when we press the start button. If the computer turns on, does the computer turn on? So this is the first action we take. We press the computer's button and we check whether it's on. If it is, we check whether there are any error messages. No errors, the computer is fine. So if there are any errors when we turn on the computer, just check what this message is about and try to fix it. If the computer does not turn on, we go to this branch of the decision, the no branch, and we check whether the power is on, the power light becomes on. If it is not, check the power cord. Okay, if the power is not plugged in, just plug it in and restart the process maybe. If it's not, if the problem is still not solved, just call a technician or call someone from the IT department. And if somehow you manage to solve your problem, check whether the computer's monitor is on. So that's another sub algorithm for your problem. Let's say you have this process of turning the monitor on. It might be something like this. Press the power button of the monitor, let's say. Okay, there's another one, and check this entire process. If it's on, if it becomes on, you might be fine, or you still see no messages. If when you press the power button of the monitor and if it doesn't light up, you need to check the power cord of the monitor itself. So these are all simplified, abstracted diagrams. Of course, this is not 100% coverage to your problem, but it's a better way of expressing the mainstream of the solution. Also, you might find these algorithms, simple algorithms, and many other algorithms that might give you a clue about algorithm design. And we have another example, which is the robotic arm. Just we want to move an arm, and we have some constraints to our problem, such as the length of the robotic arm or the rotational axis. You might be using some other transformation technique other than the Cartesian coordinates. And we provide the target coordinates as the problem parameters, and we provide the speed of movement depending on the load or depending on the urgency of our problem. And we have some solution steps, such as in which order the robotic arms motors are going to be triggered, how much turning is going to be performed, and we are going to check the security, the safety at each increments of the movement. So at each step, we just don't give the target directly, but we give the target in incremental steps, so that at every step we check whether we have arrived or there's an error, or there's a safety constraint that has been exceeded. And the output might be insecure movement, so the robotic arm movement may be terminated before it reaches the target, or the target coordinates may be reached and the process is complete. So the algorithm first receives the target coordinates, starts a movement loop such as this. Let's say we have a while loop or a for loop. There is this loop field, and within these loop block we're going to move the x-axis as much as delta x, the y-axis as much as delta y, and the z-axis as delta z. Okay, as you can see here. So if there is any insecure movement, such as the arm might hit someone somewhere, or there might be another robotic arm in the way before we complete our target movement, we might either wait or we might revert our action back. So we might move x to minus delta x to recover from those conditions. If the robotic arms are completely entangled, we might just cancel our loop and stop moving. So this is a very simplified abstraction to our movement. If the target coordinates are reached, and we might simply return that we have reached the point successfully, just leave the item or pick something from there. If we haven't reached, and if there are no security problems on our movement, we just continue with the next delta x, delta y, and delta z. And there is another simple server-client communication. So when you start a web page, when you initiate a request from a web page, we might simply establish a communication channel. And so at this step, when you try to establish a communication channel setups, there has to be a server waiting for your request. So when you establish, these two are executed together, and then after that it replies to the communication channel setup. The client sends the request data, server receives the request, processes the request, prepares a response, sends the response, and as this client is waiting for the response, server is performing 3 steps after one another, and the client receives the response data from the server in this loop, processes the response, and displays the web page's content. So this might not be a simple iteration. There may be multiple steps, maybe hundreds of other steps inside these, but just as an abstraction, you might simply draw this, practice to draw this as a flow chart, and check whether you have established the communication channel setup. If it is okay, then you might proceed with send request, okay, and then check whether you receive the response, etc. So this is one way of designing your problem with schematics.